Hello, in this lecture we're going to talk about linear regression. So the first question is, what is linear regression? Well, linear regression is a way of describing a target or dependent variable using independent variables. So what does that actually mean? So let's assume that we have a bunch of records, let's say 1,000 records. And assume that we also have some kind of a target variable that we're trying to predict. So in this case, let's assume in previous lectures we were using what does it cost you to fix your car if you get into a crash. So that's what we're trying to predict. That's our target or our dependent variable. Also, we're going to assume that we have a bunch of independent variables that are used to predict our target. So that would be things like how many traffic tickets have you had, how many miles do you drive in your car, things like that. So that's what we're going to use. And we're going to assume that there's some kind of a mathematical formula that we can apply that's going to basically be able to predict our target. So in regression, what we will do is try to come up with these weights here, these little beta values, these are our weights. We're going to try to predict those such that we minimize the error. We're going to try to get the most accurate model that we possibly can. So we're going to try to minimize our sum of squared error. Now, what does that mean? So what this means is that we have an approximation. It's not going to be a perfect model, but it's going to be a pretty good model that's going to predict, in this case, let's assume we're trying to predict damage to the amount of money it's going to cost to fix a car. Now, the method that is used to do this involves matrix algebra, and that is way beyond the scope of this class. The good news is that the matrix algebra to come up with these weights is something that computers can do at the blink of an eye. So the computer will do that work for you. You don't have to know how to do that anymore, not like you did maybe 100 years ago. So we're going to try to come up with a mathematical formula. So this still is a very abstract concept. Let's get some concrete numbers to discuss what we're doing. So let's first look at this data set right here. So what we have is we have steam, and we're going to assume that this is a factory, and the factory has a steam turbine. And what we're going to do is we want to predict steam usage in this factory. So when it's really cold out, they turn on the heater, and they're going to use more steam to heat this factory. Also, if the factory is open a lot of the days in the month, again, if the factory is open a lot, then of course we're going to use more steam. So we're going to build a model to predict steam usage given the temperature outside. So if it's cold, we're going to use lots of steam. And if we're open a lot of days, we're going to use lots of steam. So we're going to try to figure this out. So for this, we first will say that our dependent variable, this is the variable we want to predict, also called the target, is steam use. So that's what we want to predict. And our independent variables, these are the variables that we're going to input into the model, that would be the average temperature and the operating days in the month. So this is what we're going to try to use to predict steam usage. So if we put this data into R, we get this as an output. So this might look a little bit confusing at first, but it's actually quite simple. The only thing we really need to look at is the weights here. So again, we have this formula right here that we're trying to predict. So we have two input variables. We have the average temperature, and we have the operating days in the month. So we have two variables, and we want to figure out what are the weights here. So the weights from the R programming language are right here. So we have a constant term of 9.1 pound of steam. And we have here the average temperature, 0.07, negative 0.07, and the operating days is 0.20. So with this, we can plug this data in to this formula, and we're going to say that our estimate is going to be 9.12 from right there, minus 0.07 right here, times the average temperature, plus 0.2028 times x2, which is our operating days. So our formula is this. Your steam usage in the month is going to equal this mathematical formula. So how good is this formula? Well, the nice thing about regression is there are a lot of metrics that will tell us how good your model is. One of the most common ones is the adjusted R squared, or the R squared. So in this case, we start off by looking at the R squared value. And the R squared value here is 0.8491. So what does that mean? That means that our model is able to explain 84.9% of the data. A better way to think of it is just to say our model is 84.9% accurate. That's what you can think of it. That's not entirely to be precise. It's not a precise way of thinking about it, but it's a good rule of thumb. Just say our model is 84.9% accurate. Now, in the real world, they tend to use the adjusted R squared, not the R squared, but they use this guy over here, the adjusted R squared. And what that's going to do is it tends to penalize your model for having lots of variables. So the more variables you have in your model, the less desirable it is. You want a model to be simple. That's a parsimonious model. So in this case, we're going to use this guy right here. Instead of the R squared, we're going to use the adjusted R squared, which is 83.54. So you notice we got penalized a little bit because we have two variables instead of one. So the more variables you have, it starts taking the adjusted R squared value down. So when you are comparing two or more models, you will always use the adjusted R squared because that allows you to compare, let's say, a model with 5 variables and a model with 3 variables. In that case, the guy with 5 variables has a lot more variables, so it has to be much more accurate before you would want to use it. So there are actually many different metrics that people will use. You will see, of course, the adjusted R squared. This is the most widely used metric to decide how good your model is. It doesn't necessarily mean it's the best, but it is a widely used variable. Another one that is used pretty extensively is one that you will see is called the IS5213-3W6 information criteria, also called the AIC. And for the adjusted R squared, the higher the value, the better. But when you start coming into the AIC, the lower the number, the better. And again, just these metrics here will reward you for being accurate, but they will penalize you for being complicated. Now, another one that you will see, the adjusted R squared, the AIC, another one you're going to use is the Schwarz-Bayesian criteria, SBC, also called the BIC, the BIC. These two guys right here, AIC and SBC, these guys are very similar to one another, and the lower the better for these guys. They tend to be used more by pure statisticians. People in the corporate world tend to use adjusted R squared since it's easier to understand. The difference between these two guys is that this one tends to penalize complex models more than this guy. They all penalize complexity, but this guy is a little bit more of a penalty. Just because when you're comparing multiple models, you might have like 10 different regression models that you're comparing. And just because something has, let's say you're going to use the AIC value, and you say, okay, I'm going to use the AIC value to decide what the best one is. You might not choose the absolute lowest. You might choose one that is the second lowest or the third lowest. You can choose a slightly inferior model if you have a good reason. For example, let's say that it's easier to explain the second best model, or it's easier to put that model into production, or perhaps it's easier to, it uses fewer variables and those variables are less expensive to calculate. If you have a good reason, you can always choose a second or third best model. So what are the assumptions that are made in linear regression? Now, this is from a purely statistical standpoint. However, in the real world of data science, a lot of times people don't care a lot about some of these assumptions. But in a purely statistical standpoint, the assumptions that you make for linear regression are you assume independence. In other words, you assume all of the records are independent from one another. All your data is independent. You also assume linearity. So you assume that there's a linear relationship between each of the variables and your target. You also assume no multicollinearity. And you also assume that the error terms have a mean of 0 and that they are normally distributed and there's no observable pattern. Let's go through each of these real fast to see what I'm talking about. Okay, independence. What does that mean? Let's assume we're trying to predict the income of people based upon their education, their age, and their work experience. So independence, let's assume we draw a bunch of people out of a database randomly, and we pull a bunch of people, we have a bunch of customers, and we're trying to figure out if we know their age and their education and their work experience, can we predict their income so we know how to market to them? Well, here we have Mary, and she makes $50,000 a year, and she has a bachelor's degree. She's 35, and she's worked for 10 years. And Joe only makes $10,000, and he's got a high school diploma. He's 19. He's only worked for 1 year. So you see that we have here is, 6 people here, and they just randomly came out of our database. This would be independence. We just randomly drew them all out. Now, what would be a non-independent data set? Well, what would happen if instead of the data above, we accidentally only had NFL quarterbacks? So here we have Tom Brady, Joe Montana, and Joe Namath. And these guys make 10 million and 15 million and 20 million. Well, this is not independent. Over here, we've got, Joe is, high school diploma, and he's probably, working in a grocery store. And Fred, he makes 30,000, he's got a master's degree. And Dave makes 60,000, he's got a master's degree. These are people who randomly, they have nothing in common. They were just randomly drawn. But for some reason, non-independence, you can see here that we have, Mary, Jane, and Susie, they were random, but we have some sort of strange correlation or bias in the males that we drew from our database. They're all quarterbacks, and they're going to throw off our model because they all make $10 million. So we're assuming independence. We want the data to be independent, no weird patterns. What else do we see? Linearity. What does that mean? Well, we hope that the input variables have a linear relationship to the target, something like this. In other words, we had the more days that the factory was open, the more steam we used to heat the place. And over here we have a negative linear relationship. The colder it got, the hotter it gets, the less steam we use, and the colder it gets, the more steam we use. So you can see that's linear. Down here, this would be a nonlinear relationship. Sure, there's a relationship here, but this is not linear. So you couldn't use linear regression. Over here, it's just random. There's absolutely no correlation between, let's say, the average shoe size of the population and how much steam the plant uses. So over here, there's not a linear relationship, and over here, it's random. Another thing that we look at is you don't want multicollinearity. So what does multicollinearity mean? It sounds like a scary word, but it's actually quite a simple concept. You don't want your variables, your input variables, to be all correlated with one another. For example, let's assume you've got a person who makes a lot of money. He makes, $1 million a year. Well, if that guy has $1 million a year, he's probably got a lot of wealth that he has accumulated over the course of his life. He's probably, makes $1 million a year for 10 or 15 years. He's probably got $10-15 million in the bank. So he's got a lot of wealth. His car probably is a lot more expensive. He pays a lot of money in taxes. All of these things are correlated with one another. If you got a lot of income, you probably got an expensive car, and you probably got a lot of money in the bank, and you're probably paying lots of taxes. Okay, so when you have multicollinearity, what happens is if you put all of these guys into the model, you tend to get an inaccurate model because these variables are all saying the same thing and they start fighting with one another. You want to use only one of these variables, not all of them, because otherwise your model will become inaccurate, you'll overfit, it will become unstable. The parameters tend to compete with one another. So you might have a positive sign in front of income and the negative sign in front of wealth. You don't want that to happen. So you have to look for multicollinearity. Finally, you want your error terms to have an average value of 0, and they should be normally distributed like this. Also, you don't want to have any sort of pattern. We want the data to be homoscedastic. What does this mean? We mean no pattern in the data, and that's good. And so this is no pattern. If I were to look at the data right here, you can see that I have no pattern. It's just all randomly distributed. Now, if I look over here, I have a pattern, and this is heteroscedastic, and that's bad. So homoscedastic is good. It means there's random. And heteroscedastic is bad. Look, there's a pattern here. Now, heteroscedastic data, this guy right here, even though it's bad, doesn't mean you can't use the model. What that simply means is that you can make the model better. You've got a pattern here that you could probably figure it out and add more variables to the model. So again, just because you have a pattern doesn't mean you don't have a good model. It just means you can get a better model. So what if your model violates one of these assumptions, like multicollinearity, or it violates the linear assumption, or whatever? What if your model violates the assumption? Well, you can still use it. Now, let's look at a famous statistician named John Tukey. He's a very famous statistician, and he has a famous quote where he says that linear regression, what we're talking about here, is very robust. Even if you fail the assumptions, the regression model still might work to give you good results. In other words, give it a try. Basically, what John Tukey is saying is, look, even if the model violates some assumptions, you can still make money if you use it. There's another famous statistician named George Box, and his famous quote is that all models are wrong, but some models are useful. So they're basically both saying the same thing, which is, look, linear regression is pretty good, and it can give you some pretty good answers, and you can make money with it. Even if it's a little bit wrong, it's okay. It's better than pulling names out of a hat. And also, the instructor, your instructor, the opinion of your instructor is that linear regression is simple and powerful. You can use Excel to do linear regression. It's so useful. It's so easy to do. You can get away with using it in a predictive model, then do it. Even if it means taking a few liberties and violating some of these assumptions, if you can use it, do so, because it's simple to use and it's simple to calculate. So in the follow-up lectures, what we're going to do is we're going to actually see how this is done.